Okay, so I want you to look at this picture up here, and I want you to think about what happened in Algebra 2. Don't think physics right now, okay, because I got a lot of physics answers last period, which is great. We'll get there. But in Algebra 2, when you worked with equations like this and graphs like this, they were usually like launch or drop problems, right? Like you throw the ball or you launch something off or whatever, right? And you ended up with a parabola like this, right? And so this is like some king, looks like maybe he's throwing apples at his people. I'm not real sure. But if you were to throw an apple up at somebody like that, what are the chances of it being like a perfect parabola? It's probably not. I mean, probably close. But so when you were doing these in Algebra 2, your y-axis represents what? The height of whatever it is you threw. What does the x-axis represent? The time, right? If you've got a function like that, what looks up there, it's time, right? It looks like when you put it on a picture like this, like it would be the distance, right? Because you're thinking about the actual path of the apple or the ball or whatever. But the parabola that you would draw or graph or whatever was not the actual path of the object, right? Because this is, the x-axis is time, y-axis is distance or the height, okay? Then you, in physics, y'all did stuff like vertical displacement, horizontal displacement, right? And then maybe you looked at graphs like this that then the x-axis did mean the horizontal displacement and this means the vertical displacement, but they mean different things, okay? So we are going to, all you've done mathematically in your math classes are like time distance graphs. You haven't done a whole lot of, maybe you did a velocity graph in Algebra 2 if she threw in some LTF stuff. I don't remember if we do some, every now and then when I have time I'll do things like that in geometry because it kind of ties some things together. But we haven't done a whole lot of velocity and acceleration mathematically. So we're going to look at the vertical and horizontal displacements today, which have to do with a different kind of equations besides just the functions that you're used to. Okay, so I want you to think about this. We're used to thinking about time and height when we see something like this in a math class anyway, but we're going to have to write different kinds of equations to get where we need to be. All right, so let's look at the first piece of blue paper. Let me get the, which is probably, it's not even up there yet, but I got to click over here. And I'm just all out of sorts on this document camera, so you have to just bear with me. Doing the best I can. All right, we are starting with this one, and if we get to a point where you can't see what I'm doing, just make sure I know, and I'm sorry if I'm in your way, you're just going to have to deal with it. All right, so this is going to go on page 136 when we're done. And I know that this is very, very wordy, but I wanted to make sure you kind of had the example and explanation when you left out of here if you were wondering what the heck parametric equations are in the future. So this, and I'm pretty much going to read this to you too because I want to go through it. So it says algebra is really about relationships, okay? We look at functional relationships, all that kind of stuff. Relations, literally. How are things connected? Do they move together or apart, or maybe they're completely independent? So equations you are used to assume input, output, right? So like we take the input x equals 3, substitute it into this, and we observe our output, which is y equals 9. So when you talk about function machines, input, output, that sort of thing. But is that the only way to see a scenario? The setup of y equals x squared implies that y only moves because of x, because we talk about independent and dependent variables, right? Whatever's happening with y depends on what's happening with x. But it could be that y just coincidentally equals x squared, and some hidden factor is changing them both. The factor changes x to 3 while also changing y to 9. So here's an example. For every degree above 70, a store sells X bottles of sunscreen and X squared pints of ice cream. We could write the algebra relationship like this. Ice cream is equal to sunscreen squared, because that's what's happening, right? And so it's correct. The amount of ice cream is equal to the amount of sunscreen squared. It's correct, but it's misleading. The equation implies sunscreen directly changes the demand for ice cream. Like this is your input, this is your output, right? Just because you sell so much sunscreen doesn't mean that, it's not actually related to each other. So the hidden variable is the temperature that changes them both, right? So it's the temperature that's driving both things. Even though this is a correct relationship, it's not really truly what's happening in that scenario. So it's much better to write two separate equations that directly point to the causality. So we're always looking for cause. Causality is just a different form of the word cause. So sunscreen is equal to temperature minus 70, and ice cream is equal to temperature minus 70 squared. And basically that's just some, substitution stuff in there to get you to the other one. So it says the ideas temperature impacts ice cream and temperature impacts sunscreen clarify the situation, and we lose information by trying to factor away the common temperature. So when we take temperature out of there and we just get that ice cream equals sunscreen squared, we're losing information and it doesn't really make a whole lot of sense. So parametric equations, this is what we're doing today, get us closer to the real world relationship. So it says, don't think about time, just look for root causes. So this right here is the graph of the ice cream equals sunscreen squared. But again, just because you sell, however many sunscreens doesn't guarantee you the ice cream, because that's not really the direct relationship. These are the relationships, temperature to ice cream and temperature to sunscreen, right? So when you take this and you split it into two things, you make more sense of your data. So it says it's easy to have the misconception that parametric equations involve time, but the key insight is parameters point to the cause. Why did we change? The why part of that. Maybe it was time or temperature, or perhaps sunscreen really does make you hungry for ice cream. Most algebraic equations lay out connections like y equals x squared. Parametric equations remind us to look deeper. Don't get stuck in the time physics mindset. It's not always, x is not always time. And the parameter we're going to use for the parametric equations is actually t. T does not always mean time. It does not always mean temperature. It does not always mean a word that starts with t. That's just the variable that we use. Okay? Everybody good so far? Flip it over. All right. So, parametric equations supply a method of separately describing x and y coordinates. In parametric equations, the x and y coordinates are each written as a function of a third variable t called the parameter. So here's your definition of parametrics. We're going to let f and g be two functions defined on an interval I. So there's always going to be an interval there for you. The relation of all ordered pairs, f of t comma g of t, it's like your x, y, for t in this interval is called the curve C. The equations x equals f of t and y equals g of t for t in that interval are called parametric equations. Because they have parameters. And the variable t is the parameter. And it is a variable, which means it's going to vary just like x and y do. So if a curve C is defined by a pair of parametric equations, we say that the equation gives a, here's a $5 word for today, parameterization. Parameterization. It's just a different form of the word parameter, but it makes it sound smarter. Right? Gives a parameterization of C in terms of t. So we're going to look at an example that kind of talks about a real-world situation, and then some of the other things that we graph today won't have any real-world situation behind it. We're going to figure out how to graph them today. Tomorrow we're going to be able to convert them from what we're used to parametric and vice versa, and then we'll get into the actual applications and why would we even care. Okay, and we'll do that this week. All right, so we have a golfer hits a golf ball. The initial velocity and angle of elevation are used to formulate equations. So whatever you have done in physics, you have done you needed the initial velocity and the angle, right? I think they were called kinematic equations, and kinematic and parametric equations are similar. They are related, but they're not the exact same thing. I don't know if you're going to feel like they are related or not, but they're kind of related. All right, so what's missing here is the interval. I forgot to give you the interval. So the interval goes from, the t has to go from 0 to 4. So we are not even given the angle and the initial velocity right here. We will eventually, we're just told this is how they came up with them. We'll learn how to come up with them later. So here are the two things, x of t and y of t. So when you have your t table, that's literally now a t table, you have 3 columns instead of just 2. And our t here goes from 0 to 4, so we're going to put in 0, 1, 2, 3, 4. And then our x of t, that means we just substitute 0 in here, we get 0. When you substitute 1 in here, you get 130. 2 gives you 260, then 390, then 520. How many of you did 4 times 130 to get that? Couldn't you have just added 130 to 390? Think about that. Think smarter, not harder. Okay, so when I take 0 and I substitute it into here, I get 0, right? When I take 1 and substitute it in here, I'll have a negative 32 and a positive 130. What does that give me? 98. Okay. I'm just going to go ahead and give you the other ones. I know you're capable of figuring them out, but instead of us taking the time to do that, I'm just going to go. They're not even that hard, but it's just not worth the time when I know you're capable. So that's what you would get when you substitute. I just want to make sure you know where I'm getting them from, substituting them in. Okay, so over here, we need when we have our little graph here, t does not get graphed. X of t and y of t get graphed. Your x of t is going to represent your horizontal distance. Okay, so this is your horizontal distance, which is x of t. Or it's also displacement, kind of the same thing. We're going to talk about distance and displacement, actually. It's really more your horizontal, it's your distance here and your displacement, but we'll get to the others. So then this is your vertical distance, which is y of t. Okay. Everybody good so far? We need to mark off this axis. So let's see, x is going to go to about 520, so we'll make this 500. And then just separate them as much as you can. That is not good at all, but mine's really bad. Maybe I shouldn't have started with the end. Try and space them out. And I used a pen. I can't even fix it. So each one of them is 100. And so then going up this way, my y goes to 132. So we'll just make that go to like 150. So then remember, the t's don't get plotted. It's x of t and y of t. So my first order pair is 0, 0. There's a point. My next order pair is 130, 98, which would be right about there. Then I go to 260 and 132, 390 and 102, 520 and like 8, something like that. Hopefully yours looks better if your little hash marks are more spaced out than mine. All right, so I'm going to sketch this in. There are not arrows on the end, okay? There's no arrows on the end. It doesn't go on forever. I had an interval that goes from 0 to 4, okay? That's it. But there are some arrows on here, just not the arrows on the end to say that it goes on to infinity. Instead, you need a direction of movement here, meaning I started here at t equals 0, and then I went to this direction. These little arrows, this actually shows the path of the ball itself. And it was going in this direction, not coming towards me. Okay, so those arrows are important on there. Okay. Any questions at all? We're all good? All right, grab your other piece of paper. It's going on page 137. This explains some of the same things, but I liked some of the explanations on the other one too. That's why I'm just giving you two. All right, so a baseball is thrown in the air. We have this function f of t equals 40t, represents the horizontal distance. That means it's also like my x of t. The ball has traveled after t seconds. The function g of t equals all of this, represents the vertical height of the ball after t seconds. So here they are graphed separately. This is the graph that you are used to doing, like in Algebra 2 or mathematically anyway. And this horizontal distance really just doesn't even get talked about. But it's important, and so we kind of put these two things together on one graph. Okay, so it says to show both the vertical height and horizontal distance on the same graph, we can use parametric equations. F of t and g of t are continuous functions of t on the interval I. Then the corresponding parametric equations are defined as, it's exhausting, right? X equals f of t, and y equals g of t. Okay. Everybody good so far? All right, and they are continuous functions. T is called the parameter. I is called the parameter interval, sorry. And then the ordered pairs f of t, g of t gives us the parametric curve to relate the two things together. All right. So it says write a set of parametric equations for the scenario above, then complete the table and sketch the graph. So since f of t equals 40t and g of t equals this, and x equals f of t, y equals g of t, then we know that x equals 40t and y equals negative 16t squared plus 48t plus 64. The interval is missing off of this one too, so you don't get to make them up. They'll be on the other ones. 0 is less than or equal to t, which is less than or equal to 4. Okay. All right, and let's put our t's in here. This is 0, 1, 2, 3, 4. So x would be, when I substitute t in here, I'm going to get 0, and then what? 40, 80, 120, 160. All right, so then when I substitute 0 into this one, what do I get? Nope, I get 64, yeah. And again, I'm just going to give you the rest of them because we don't need to take the class time. Y'all figuring it out. I know you're capable of it. I'm not worried about it. 64 and 0. So then we need to label our axes. Right? It told us in the information up here that this is the horizontal distance, which is our f of t, and this is our vertical height, which is our g of t. And then if we mark these off, we can make every space 10. So I can go to 1, 2, 3, 4. Make this 50, 60, 70, 80, 90, 100, and 150. And do the same thing going up. It's 50, 10, 20, 30, 40. Okay. Everybody okay with that so far? Good? Sorry, I know I'm in the way. All right, so then we're going to graph. I'm going to go to 0, and then 64, somewhere right about there. I'm going to go to 40, 96, and go to 80. It's also at 96. 120 is at 64 again. And 160 is at 0. Okay, so there are my points. I'm going to put the dotted line in there. I'm going to show you a different thing that can be done besides the arrows. We're going to do the arrows. That is what I want from you. But I just want, if you ever see it differently, it kind of gives you the same thing. Remember, there's not arrows on either end because it is stopping right where it is. But I could label each point and say, okay, well, this one was t equals 0. This one is t equals 1. This one is t equals 2. T equals 3. T equals 4. So if I do it this way, there's no question the direction of movement without arrows, right? It's just a different way to do it. Everybody good so far? Any questions at all? I can label them like that instead of doing the arrows. That's not what I want from you every time. I just want you to see it and know that it could be that way, because that gives me my direction of movement. Kind of lets me know where the T was as well. What are we having trouble seeing? I can see y'all squinting. I don't know how to zoom in. What? This is T of 0, T equals 1, T equals 2, T equals 3, T equals 4. Just label those points. Because of the interval, yeah. That's right here. I know, it's not very bright, and I don't know how to change that on this one. Yeah, but I don't think that doesn't change the brightness of the, it doesn't change the brightness of this. Oh, I just took a picture. Yeah. It's this that's the issue. It's our cheap projectors. I keep taking pictures. Okay. All right, flip it over. Let's use the back of another one. All right. Let's look at number 2. All right, and on here I should have put little charts for you and I didn't, so we need to make a little t-chart. And this time, this is going from -4 to 4. So my t, my x of t, my y of t. So I've got -4, -3, -2, -1, 0, 1, 2, 3, 4. All right, so if I take -4, substitute it into t, what's -4 squared? 16. Minus 7 is 9. -3 squared is 9. Minus 7 is 2. -2 squared is 4. Minus 7, -3. -1 squared is 1. Minus 7 is -6. 0 gives me -7. Now, when I square 1, 2, 3, and 4, am I going to get the same thing I did when I squared -1, 2, 3, and 4? Yep, so this is going to go -6, -3, 2, and 9. So then I substitute -4 into the y equation. -4 divided by 2 is going to be -2 plus 5 is 3. -3 divided by 2, we'll go ahead and use decimals here because they'll be pretty decimals. -3 divided by 2 is 1.5, or -1.5 rather. And then plus 5 gives me 3.5. And then it's just, these are just going to increase by 0.5. So then it's 4, then it's 4.5, and then it's 5, and then it's 5.5, 6, 6.5, and 7. Okay. Again, I know you're capable of finding them, so there's no use in us taking the class time to figure out those values. Okay, so now we're going to graph them on this little teeny tiny grid. It's hard for me to read. We have nothing to label the axes at because these are just equations that they gave us. We don't necessarily know what applies to it, so we're not labeling the axes. We're just plotting the points to get used to these graphs, and then we'll get to what it actually means in a little bit. All right, so just go ahead and plot these points. Remember, you're only plotting x and y, not t. All right, so that you can, I don't think you necessarily need me to talk you through plotting them, hopefully. So I'm going to go to... Remember, the endpoints should be points. There's not arrows going on, but I do need arrows to show the direction of movement. So I started over here. My arrows should look like this. Yeah, it's skinny in the graphs, and the lines are really teeny tiny here. Dotted lines, it doesn't really matter. No. Yeah, it's either solid or dotted, it doesn't matter. Mine are just dot. I can get them a little bit better if they're dotted. Okay, any questions at all? I know. Are we all good? Yes? All right. Well, if you are, or even if, once you get there, we're skipping number 3 because it's mean without a calculator. You're going to do number 4. Okay, all on your own. So if you're done with number 2 and you've checked yourself, and I'll come and check and make sure you're good, then do number 4. As soon as you're finished with number 4 and I check it and you agree with me, then I will give you your assignment. On the assignment, you are only doing the 4 graphs on the top right now. Tomorrow's lesson is the rest of it. That's why it's not due until Friday. Okay, but you could get the graphs done if you wanted.